I'll now invite Dr. Waliur Rahman from NCPUR to talk about the predicting tipping point for the future collapse of Antarctic ice sheet.
Okay, so I am going to talk about West Antarctic ice sheet, which is now currently undergoing rapid mass loss, and it is expected that at some point of time it is going to be collapsed, and which has a catastrophic consequence. So then the question is when and how much. So it is quite uncertain. So there are model prediction, but again I will take back in a geological time scale when the CO2 was very high, SST was, or atmospheric temperature was very high, and then we'll see how the West Antarctic ice sheet was, and probably that information will help us to understand how the West Antarctic ice sheet is going to be in the near future climate. So okay, I'm not going into, okay, now if you see the West Antarctic ice sheet, there are two major glaciers which is undergoing rapid mass loss. One is Pine Island and then Thwaites, and which we say it's a weak underbelly of the West Antarctic ice sheet. And then let us see that how much contribution actually coming from the different parts of Antarctica. If you see the East Antarctica does not contribute to the sea level rise, Antarctic Peninsula it's little bit, but most of the contribution to the sea level rise is actually coming from the West Antarctica. It's almost a centimeter per decade. So then the projection for the sea level rise, if you see, it's almost at the end of the century, it's a meter sea level rise. And then, so if you see that the projection, then the future is going to be havoc. So many of the coastal cities worldwide, even in India, if you see, few feet of sea level rise going to be havoc to these cities. Now, question is that how much and how fast this West Antarctic ice sheet is going to be collapsed, and what are the tipping points at which the ice sheet is going to be collapsed. For example, atmospheric CO2, temperature and time of collapse. So there are some model at different CO2 scenario by Decant and Pollard, and so if you see the top one is the minimum scenario of the CO2 RCP, which is basically the CO2 level pre-industrial, almost you can see the normal condition, and the extreme scenario if you see RCP 8.5, which is almost complete collapse of the ice sheet. And then there are also model which also reconstructed the past. It's one of the reconstruction for the last interglacial period, which is considered to be the warmer period than the Holocene. And if you see that production it was almost completely ice free West Antarctica. And then this is one of the geological interval which is of our interest, which is Pliocene, and which is the interval of 5.3 to 2.6 million year in a geological interval. So this particular interval is considered to be the best analog for near future climate, because CO2 was 400 to 450 ppm of CO2 and SST was 2 to 3 degree temperature higher. So let's see, this is a model prediction for the Pliocene, and if you see at 400 ppm of CO2, 3 degrees Celsius higher temperature than the pre-industrial, you can see that's a complete collapse of the ice sheet. But the question is how to validate this kind of a model prediction or the simulation, what are the sources of uncertainty, and then how to test the assumptions involved in those simulations. So one of the first attempt that was made by the Wilson, basically what they did, they take a sediment core close to the East Antarctic ice sheet and they reconstructed the erosion history based on the neodymium isotope records, and then they found that the extreme changes in the erosion, basically it's associated with the ice sheet dynamics. So there are two sources of the sediments, one interior and the coastal, and interior which is more radiogenic and then coastal is the less radiogenic, and this change in the erosion. So basically what happened during the glacial period, interglacial period, the ice sheet melted and it went up to the interior, and sediments used to derive from the interior of the East Antarctica, and then glacial condition when the ice sheet expanded, then the interior sediments were locked. The sediments used to come from the coastal. So the erosion, extreme erosion changes during the glacier interglacial is closely linked with the Antarctic temperature. So we have a nice record from the Antarctic ice core record, and they determine the tipping point for These changes is for the East Antarctica that was 2 degrees Celsius higher than the pre-industrial, and if that temperature sustained for 1,000 years to 2,005 years, 2,500 years, the ice sheet is going to be collapsed. So that was the tipping point, and the approach was given in this paper. So, but then nothing exists for the West Antarctica. So what we did, we participated in one of the expedition which was to the Amundsen Sea to get the record near to the close of the West Antarctic ice sheet, and I participated in that expedition, and using the same approach we have reconstructed the erosion history based on the neodymium isotope records. So here there are two ice sheets, as I said, the Pine Island and Thwaites, and the lithology of the Pine Island is the more radiogenic sediment, so whereas the Thwaites is the Pine Island is less radiogenic, Thwaites is more radiogenic. And if you see during the Pliocene interval, the sediments mostly used to come from the Pine Island, and even it was connected to the East Antarctica. So because East Antarctica sediments is less radiogenic. So during the Pliocene, ice sheet was completely ice free, and then sediments used to come from the Pine Island as well as the East Antarctica. When the situation shifted to the Pleistocene, which is basically ice house condition or cold condition, you can see there is no change in the erosion, a stable ice sheet. So now we can compare with this with the forcing factor and then sea level, and the way the Wilson has done in the Nature paper. So here if you see the close look of temperature and then the erosion history, you see during the Pliocene when there was a complete collapse, we can see the temperature 2 to 3 degrees higher, and when it's entered in the Pleistocene, even though there is a drop, but at the same time we have a large glacier interglacial variation in the temperature, but interestingly you don't see in the change in the erosion, and it means the ice sheet was stable. The CO2 during the Pliocene, it's a 400 to 450 of CO2 ppm, but during the Pleistocene you have a large variation 180 to almost 300 ppm of CO2, but this was during that variation, even then the ice sheet was stable. So that is quite surprising. So now to conclude, so during the Pliocene, when the CO2 was higher 400 to 450 ppm and 2 to 3 degree temperature than the pre-industrial, we have seen the complete collapse of the ice sheet. But when the ice sheet entered in the Pleistocene condition, when you have a very large variation of the CO2 and then large variation of the temperature within the limit of this, the ice sheet did not change. So ice sheet was stable. So this is big surprise. It means whatever the changes we see, this is a recent. It's not the part of the long-term change. So we can set the limit for the West Antarctic ice sheet. At this stage, we can say the Pleistocene condition was the limit for the West Antarctic ice sheet stability. So Pleistocene temperature, CO2 orbital forcing are the maximum limit for the stability of the West Antarctic ice sheet. Though it can be tuned a bit more, but at this stage I can make the statement like this: the Pleistocene condition was the limit for the stability of the West Antarctic ice sheet. That's all from my side. Thank you.